Hello students, welcome to the course on Advanced Communication Systems and the course code is EC 801. This is a 3 credit course and this is for BTech 8 semester EC students. Myself, Dr. Shurojit Boshak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata, and this is my official email address. In the last class, we have started module number 3, that is spread spectrum communication. We have discussed about what is spread spectrum, why it is needed, and what are the applications of spread spectrum communication, and what are the different types of basic notions of spread spectrum, basic principles of spread spectrum, and what are the different types of spread spectrum communications are present. So that are typically two types already I discussed, that is direct sequence spread spectrum and frequency hopped spread spectrum signal. Now today we are going to discuss in detail about these two types of spectrum communication, and the lesson objective of this topic is to understand the purpose of spread spectrum, the challenges it overcome, and the advantages it provides for commercial applications of digital communication. And this topic is mapped with CO number 3 and CO number 4. So let us start lecture number 2 from the module 3, that is spread spectrum communication, with the topic of direct sequence spread spectrum. This is the first figure which depicts the transmitter of direct sequence spread spectrum. It first converts the incoming binary data sequence, say BK, into a polar energized waveform BT, which is followed by two stages of modulation. The first stage consists of a product modulator or multiplier with the data signal BT and the PN signal CT. PN signal means which represents the PN sequence as these two are the inputs of the product modulator. The second stage consists of a binary PSK modulator. The transmitted signal XT is thus a direct sequence spreads binary phase shift kit waveform, that is DS BPSK signal. This is the receiver, which consists of again two stages of demodulation. In the first stage, the received signal YT and a locally generated carrier are applied to a product modulator followed by a low pass filter whose bandwidth is equal to that of the original message signal, that is MT. This stage of the demodulation process reverses the phase shift keying applied to the transmitted signal. The second stage of demodulation performs spectrum dispreading by multiplying the low pass filter by multiplying the output of the low pass filter by locally generated replica of the PN signal, say CT, followed by integration over a bit interval 0 to t b, and finally a decision making process or a decision device is present, and where a threshold is given, and this consists of 1 if threshold exceed, otherwise it is 0. So this is the receiver of DS spectrum with BPSK signal. This is the waveform of modulated signal. First, this is the product signal, that is MT equal to CT into BT, and this is the carrier signal. So these two signals are BPSK applied to a BPSK modulator, which is shown here. Here from here 0 to 1, so one phase shift is present. See, then again 1 to 0, another phase shift. Then here 0 to 1, so again another phase shift. So 3 phase shifts are present in this waveform. Now this figure is a model of direct sequence spread binary PSK system. Here, see the channel output, that is YT, is basically XT plus JT. Now XT is basically the multiplication of ST into wideband PN signal, that is CT. Now output, that equals coherent detector input, that means UT is basically is a product of YT into CT. Now by putting the value of YT from here to here, that is now C square T ST plus CT into JT. Now C square T is 1 for all values of T. So this is now ST plus the noise CT into JT. So this is UT, and apply the local carrier, it can estimate the original signal. Now here, another thing is that synchronization, another issue. How this circuit can properly operate. So a synchronization issue is present. For its proper operation, a spread spectrum communication system requires that the locally generated PN sequence used in the receiver, see here, used in the receiver to display the received signal must be synchronized to the PN sequence used to spread the transmitted signal in the transmitter. A solution to the synchronization problem consists of two parts. One is acquisition and tracking. In acquisition, the two PN codes are aligned to within a fraction of the chip in as short a time as possible. Once the incoming PN code has been acquired, tracking or fine synchronization takes place. Typically, PN acquisition proceeds in two steps. First, the receive signal is multiplied by a locally generated PN code to produce a measure of correlation between it and the PN code used in the transmitter. Next, an appropriate decision rule and search strategy is used to process the measure of correlation so obtained to determine whether the two codes are in synchronization or not. As for tracking, it is accomplished using phase lock techniques very similar to those used for the local generation of coherent carrier references. The principal difference between them lies in the way in which phase discrimination is basically implemented. Okay? So synchronization is a must be required between these two PN codes. Next is frequency hop spread spectrum. What is frequency hop spread spectrum? In the type of spread spectrum system discussed in earlier, the use of a PN sequence to modulate a phase shift key signal achieve instantaneous spreading of the transmission of bandwidth. The ability of such a system to combat the effect of jammer is determined by the processing gain of the system, which is a function of the PN sequence period. The processing gain can be made larger by employing a PN sequence with narrow chip duration, which permits a greater transmission bandwidth and more chip per bit. However, the capabilities of physical devices used to generate the PN spreads spectrum signals impose a practical limit on the attainable processing gain. It may turn that the processing gain so attained is still not larger enough to overcome the effects of some jammers. So, what are the alternative methods? The alternative method is to force the jammer to cover a wider spectrum by randomly hopping the data modulated carrier from one frequency to the another. In effect, the spectrum of the transmitted signal is spread sequentially rather than instantaneously. The term sequentially refers to the pseudo-random ordered sequence of frequency hop. The type of spread spectrum in which the carrier hops randomly from one frequency to another is called frequency hop spread spectrum. A common modulation format for FH systems is that MRE FSK or MRE frequency shift keying. The combination of these two techniques is referred to as simply FHM-FSK. Since frequency hopping does not cover the entire space spectrum instantaneously, we are led to consider the rate at which the hops occur. Therefore, we may identify two basic characterization of frequency hopping. One is slow frequency hopping and other is fast frequency hopping. In slow frequency hopping, here symbol rate Rs of the MFSK signal is an integer multiple of the hop rate RH. That means several symbols are transmitted on each frequency hop. And in first frequency hopping, hop rate RH is an integer multiple of symbol rate Rs. That means the carrier frequency will change or hop several times during the transmission of one symbol. So first we go for slow rate frequency hopping. This is the figure for the transmitter of slow frequency hopping, which involves frequency modulation followed by mixing. First, the incoming binary data are applied to an MRE FSK modulator. The resulting modulated wave and the output form a digital frequency synthesizer are then applied to a mixture that consists of a multiplier followed by a bandpass filter. The filter is designed to select the sum frequency component resulting from the multiplication process as the transmitted signal. In the receiver, this is the pictorial diagram for the receiver of slow rate frequency hopping. So in the receiver, the frequency hopping is first removed by mixing. The received signal with the output of a local frequency synthesizer that is synchronously controlled in the same manner as that in the transmitter. The resulting output is then bandpass filtered and subsequently processed to a non-coherent MRE FSK detector. This is the variation of this is an example. This figure illustrates the variation of the frequency of a slow FHM-FSK with time for one complete period of the PN sequence. The period of the PN sequence is 2 to the power 4 minus 1, that is 15. The FHM-FSK signal has these parameters. Number of bits per MFSK symbol K is equal to 2. number of MFSK tone, that is capital M, equal to 2 to the power caps K, that is 4, and length of the PN segment per hop, small k, denoted as small k, which is 3, and total number of frequency hop, 2 to the power k, which is 8. Now see, in this example, the carrier is hopped to a new frequency after transmitting, see, two symbols or equivalently 4 information bits. This figure also includes the input binary data and the PN sequence controlling the selection of frequency hop carrier frequency. There are 8 distinct frequencies available for hopping. Only 3 of them are utilized. And this is the variation of the d-hopped frequency with time, this figure. Now see, from 0, 1 to 1, 1, this is for 0, 1 to 1, 1. So 4 information bits or 2 symbols. So this is for 1 frequency, this is 1. Now here it is for, in all the cases, these two are slightly different, but here it is same. Because see, in the last 4 cases, 1 0 1 0, same code, 1 0 for the first 2 bit and second 2 bit is 1 0, and for PN sequence is same, that is for 0 0 1, that is why it is same. Okay. Now moving for the first frequency hopping. A fast FHM FSK system differs from a slow FHM FSK system in that there are multiple hops per MRE symbol. Hence, a fast FHM FSK system, each hop is a chip. In general, fast frequency hopping is used to defeat a smart jammer's tactics that involves 2 functions: measurement of the spectral content of the transmitted signal and returning of the interfering signal to that portion of the frequency band. Clearly, to overcome the jammer, the transmitted signal must be hopped to a new carrier frequency before the jammer is able to complete the processing of these 2 frequencies. For data recovery at the receiver, non-coherent detection is used. However, the detection procedure is quite different from that used in a slow FHM FSK receiver. In particular, 2 procedures may be considered. For each FHM FSK symbol, separate decisions are made on the K frequency hop chips received, and a simple rule based on majority vote is used to make an estimate of the d-hopped MFSK symbol. And the second is, for each FHM FSK symbol, likelihood functions are computed as functions of the total signal received over K chips. and the largest one is selected. Now, this is an example of variation of the transmitted frequency of a fast FHM FSK signal with time. This signal has the following parameters. Here, the number of bits per M FSK symbol, capital K, is 2. Number of M FSK tone, that is capital M, which is 2 to the power K, caps K, which is 4. And length of the PN segment per hop, K equal to 3. And total number of frequency hops, that is 2 to the power small k, which is 8. Now, see, in this example, each MFSK symbol has the same number of bits and chips. That is, the chip rate, say RC, is same as the bit rate RB here. After each chip, the carrier frequency of the transmitted MFSK signal is hopped to a different value, except for few occasions when the K chip segment of the PN sequence repeats itself. So this is all about direct sequence and frequency hop spectrum. In the next class, we will start the multiple access techniques. That is one of the most important application of spectrum. So thank you.